Hi, today we are going to talk about nuclear chemistry. What is nuclear chemistry? Well, before we can answer that, first we need to know some notation. This is a carbon-12 atom. It is the standard isotope of carbon. This is the standard representation for it on the periodic table of elements. You see that the mass, the number of protons and the number of neutrons added together, is at the bottom, and the number of protons is in the top right. That is the atomic number. This can be represented for nuclear notation by putting the 12 at the top beside the C and the 6 on bottom. You can also write this as carbon-12. Nuclear chemical reactions, like the one shown here, where carbon-13 decays, must follow the first law of thermodynamics, that energy cannot be created or destroyed. This means, like in normal chemical reactions, that values have to add up. The carbon-13, which is a radioactive species of the carbon atom, decays to become a more stable isotope. Isotopes are subclassifications of elements based on the number of neutrons they have. So it decays to carbon-12. But wait, where does the extra mass go? It is released as a chargeless neutron, as shown here. Electrons are represented as having zero mass because their mass relative to a proton is too negligible to be considered. Positrons are the antimatter equivalent of electrons. They have the same mass, but opposite charge. Do you see how this notation for subatomic particles follows from the general nuclear notation? So, what is nuclear chemistry then? Nuclear chemistry is the study of the behavior of the nucleus of atoms. Generally, one is studying the radioactive decay of nuclei as they seek to reach a stable configuration. There are three major kinds of radiation that nuclei release: alpha particles, beta particles, and gamma particles. Alpha particles are simply positive helium nuclei, which are released to reduce both the mass and the charge of the atom so that it will be below the band of stability. Beta particles can be either positive or negative, and they are positrons and electrons in essence. They are released to raise or lower the charge of the atom. Gamma rays, or gamma particles, are simply electromagnetic radiation that are often released with the others to equalize energy between different values. There's also a such thing as electron capture. Electron capture is when an atom absorbs an electron so that it will reduce its charge. But wait, why do atoms need to decay in the first place? The answer is actually quite simple. This is a drawing of a graph that shows the isotopes of stable nuclei. You will see that there is a pattern to the number of neutrons versus the number of protons. They seem to average approximately 1.2, favoring the protons more as you move down the chart and neutrons more as you move up the chart. Why is this the case? Remember, protons are actually very repulsive to each other. Only strong nuclear force, for which neutrons help mediate, hold nuclei together. Hence we see the band of stability that corresponds roughly to the 1 proton, 1.2 neutrons line, with more massive atoms favoring the higher side, as aforementioned. So, let's do a problem. Predict the mode of decay for carbon-14, for xenon-118, and for plutonium-246. Well, in order for each of these atoms to reach the magical proton-neutron ratio, what has to happen? Carbon-14's neutron content must go down, or its proton count must increase. Alpha particles are too large to be a frequent form of decay for small atoms. Electron capture reduces the charge of the nucleus, the opposite of what we want. Likewise, with the positive beta emissions, the same effect occurs. But negative beta emissions raise the charge without changing the mass. This is what we want. What about xenon-118? Xenon-118 actually has a neutron-to-proton ratio of 1.2, but it is high enough in both mass and charge that it needs a steeper ratio than that. Both electron capture and positron emission raise the neutron-to-proton ratio. Plutonium-246 is outside the stable realm of atoms, and needs both lower mass and lower charge to be stable. The fastest way to achieve this is by alpha particle emission. But the same plutonium atom will need to decay repeatedly to become stable. These are the atomic reactions for the aforementioned atoms that are once successfully written out and balanced. A final question you will need to be asked when you study nuclear radiation revolves around half-life. Half-life is the amount of time it takes a sample of a radioactive substance to decay so that only half of the substance is radioactive of that given isotope. The half-life of any constantly decaying sample, which all nuclear decaying samples are, is given by the value natural log of 2 over r, where r is the rate of decrease and e is the rate of constant growth. A proof is shown here. Well, that's all we have to study for nuclear chemistry today. I'm glad that I could help you, and I hope that you can apply your chemistry and edify your mind further as you go through your chemistry career.